let's focus on how to simplify a force and couple system in 3 dimensions. Now, in the previous lesson, we said that a system of several forces and couple moments acting on a body can be reduced to an equivalent system consisting of a single resultant force acting at a specified point and a resultant couple moment. Now, let's consider the case where we have 2 forces acting on the body. So we have this to be the body, and then we have 2 forces, F1 and then F2, acting on the body, and we have this to be point O. Now you realize that the line of action of the 2 forces does not pass through O. Hence, it is very important or necessary that we define position vectors directed from O to the line of action of each of the forces. So we are going to have position vectors R1 and then R2. Again, let's also assume that we have a couple moment, say M, also acting on the body. Now, couple moments are usually free vectors, hence they can act anywhere on the body. Now, for the sake of conveniency, let's direct it away from O. So we are going to assume that this couple moment M is directed away from O. Now, in that case, we can obtain an equivalent system which produces the same external effects on the body as that of the original force and couple system. So we can sum up the forces and couple moments as we can have the sum of all the forces in this system as the resultant force equals, we have F1 plus F2, and then the resultant couple moments MR of O. So that happens to be the resultant couple moment about O. So that is equal to M plus M1 plus M2. Now, M1 and M2 are the couple moments as a result of the forces F1 and then F2. So to find M1 and M2, we say that M1 is equal to the cross product of R1 and F1, and then M2 is also giving us the cross product of R2 and F2. So finally, if we consider this to be the body with a point O somewhere here, then you are going to have this to be the resultant force FR, and then you have the resultant couple moment about O somewhere here. So that is MR of O, and this happens to be the angle theta. Probably there is a clockwise rotation. So basically, these are the 2 main equations we are going to use to simplify a system of several forces and couple moments to an equivalent system. Now let's try a few examples. So let's consider this example, that is example 1. We are going to replace the loading system by an equivalent resultant force and couple moments acting at point O. Now, usually when you are given a question like this, the first thing you are supposed to do is to represent or express the forces given in the question and the couple moments M as Cartesian vectors. Now, looking at this question, we already have F1 and then F2 already expressed as Cartesian vectors, and we don't have any couple moment M. So we have F1 as negative 300I plus 150J plus 200K. And then we have F2 also to be negative 450K. And then we don't have any couple moment M, so that is 0. Now, having done this, the next thing we are going to do is to replace the force and couple moments with an equivalent system. So first of all, we are going to deal with the forces. So let's find the resultant force. So that is giving us FR equals F1 plus f2. So that is equal to, we have f1 to be negative 300i plus 150j plus 200k, and then for f2 we have negative 450k. So let's sum them up. So we are going to have negative 300i plus 150j, and then here we have 200k minus 450k, so that becomes negative 250k. So this happens to be the resultant force Fr. Now let's move on to the resultant couple moment about point O. So for the resultant couple moment, which is given by mr of O, that is equal to m plus m1 plus m2. So in order to evaluate this, we first of all need to find the values of m1 and then m2. So for m1, that is given as the cross product of r1 and f1. Now r1 represents the position vector directed from O to the line of action of the force F1. Now the line of action of the force F1 passes through point B. So we are going to define position vector directed from O to point B. So that is R1. Now to move from point O to point B, we need to move some distance along the z-axis, along the y-axis, and along the x-axis. So along the z-axis, we are going to move away from point O to this point, and that's going to be 1 meter. So we have k, 1 times k is k, and then from this point moving along the y-axis also away from point O, we are going to have a positive value, which is 2 meters. So that becomes 2j, and then from this point through to point B, we are going to move a distance of 1.5 meters. However, that is along the negative x-axis, so it becomes a negative value. So this is negative 1.5 I. So we have R1 to be negative 1.5 I plus 2j plus k. So we have this cross. Now for F1, we have negative 300I plus 150j plus 200k. So let's resolve this. So we have the 3 by 3 matrix, where the first row contains the unit vectors directed along x, y, z. So we have I, j, k, and then for the second row we have the values of R1, so the coefficients. So that becomes negative 1.5, 2, 1, and then that of the force comes at the third row. So we have negative 300, 150, 200. Let's solve this together. So we pick I, we cancel out the row and column containing I. We have 200 times 2, that is 400, minus 150 times 1 is still 150, so minus j. We pick j, we cancel out the row and column containing j. 200 times negative 1.5 is negative 300, minus negative 300 times 1 is negative 300, so it becomes plus 300, and then plus k. We pick k, we cancel out the row and column containing k. 150 times negative 1.5 is negative 225, minus negative 300 times 2 is negative 600. So it becomes plus 600. Hence we have I times 250 minus j times, this becomes 0, plus k times positive 375. Therefore, we have m1 to be equal to 250i plus 375k in Newton meter. So that is for m1. Now let's move on to m2. So for m2, we have m2 to be equal to r2 cross f2. So that is equal to, we also define position vector directed from O to the line of action of f2. Now this is the line of action of f2. So we can simply define the position vector from O through to this point. So that is r2. And you realize that this is acting along the positive y-axis. So we only have a positive y component. So that's going to be 2 meters, and that is 2j. So we have r2 only to be 2j cross f2 is negative 450k. So that will be equal to, we have I, j, k, and then 0, 2, 0, and 0, 0, negative 450. So this is equal to, we select I, we cancel out row and column containing I, we have negative 450 times 2, that is negative 900. 0 times 0 is 0, so minus j, we cancel out row and column containing j, negative 450 times 0 is 0, 0 times 0 is also 0, plus k. We cancel out row and column, 0 times 0 is 0, 0 times 2 is also 0, so we are left only with negative 900i. Therefore we say that m2 is equal to negative 900i. Now, to find the resultant couple moment about O, we have mr of O to be equal to m plus m1 plus m2. So we already have m to be 0, so 0 plus m1, that is 250i plus 375k plus m2, which is giving us negative 900i. Now let's simplify this. So this becomes 250i plus negative 900i gives negative 650i, and then plus 375k. So this happens to be the resultant couple moment about point O. Now let's move on as we solve the next example. Now for example 2, we are also going to replace the loading system by an equivalent resultant force and couple moment acting at point O. Now for this question, we are given the magnitude of the forces and the couple moment. So the first thing we are going to do is to express each of these three quantities as Cartesian vectors. So we are given F1 to be 100 newtons. So as a Cartesian vector, you have F1 to be equal to the magnitude of F1, which is 100, times the unit vector directed along the force. Now the force is directed along the y-axis, and the unit vector directed along the y-axis is g. Now this happens to be along the negative y-axis, hence we are going to have negative j. So we have 100 times negative j, and that is equal to negative 100j. Now also for f2 is directed along the xz plane. So if you want to get to f2 from this point, you need to move some distance along the z-axis and some distance along the x-axis. And so we are going to have the magnitude of f2, which is 200, times the unit vector directed along f2. So from this point, we move some distance along the z-axis, and then downwards means that we are going to have a negative value. So that's going to be negative 0.3k. And then from this point, you move along the negative x-axis, and that means that you have a negative value, that is negative 0.4i. So you have negative 0.4i minus 0.3k, all divided by the square root of negative 0.4 square plus negative 0.3 square. Now if you resolve this, you have 200 times negative 0.4i minus 0.3k, and the denominator becomes 0.5. 200 divided by 0.5 is 400. So you have 400 times negative 0.4i minus 0.3k. And finally, 400 times negative 0.4 is negative 160. 400 times negative 0.3 is negative 120. So that happens to be f2. Now also for m, we have m directed along the negative x-axis. So that's going to be negative 75i. So this is f1, this is f2, and then this is m. Now straight away, we can find the resultant force Fr. So Fr is equal to F1 plus F2, and that is equal to, we have F1 to be negative 100J plus F2 negative 160I minus 120K. Adding these two quantities, you are going to have negative 160I minus 100J minus 120K. So this is the resultant force. Now let's move on to the resultant couple moment about point O. So that is also giving us MR of O equals M plus M1 plus M2. Now we already have M to be negative 75I. Let's find the values of M1 and M2. So for M1, it is equal to the cross product of R1 and F1. Now R1 represents the position vector directed from O to the line of action of F1. So this is R1. This is the position vector R1. So from this point, if you want to move along the z-axis to touch this force, then you are going to move 0.3 meters upward. So we have 0.3 k. So we have 0.3 k cross F1, which is negative 100 J. So that will be equal to, we have I, J, K. Next we have 0, 0, 0.3, and then lastly 0, negative 100, 0. So let's work out this. So this will be equal to, we select I, we cancel out row and column containing I. 0 times 0 is 0, minus negative 100 times 0.3 is negative 30. So it becomes plus 30, minus J, we cancel out row and column containing J. 0 times 0 is 0, 0 times 0.3 is also 0, plus K, we cancel out row and column. Negative 100 times 0 is 0, 0 times 0 is also 0, and then you realize that we have M1 to be equal to 30I. M1 is equal to 30I. Now let's move on to M2. So for M2, M2 is also equal to R2 cross F2, and that is equal to we are going to define position vector directed from O to F2. So we are going to move some distance along the y-axis and some distance along the z-axis. So along the y-axis we have a positive value of 0.5, and then along the z-axis we also have a positive value of 0.3. Now in all cases we are moving away from point O, that is why we have positive values. So we have R2 to be 0.5 J plus 0.3 K cross F2, we have negative 160I minus 120K. So that is F2. So let's simplify this. We are going to have I, J, K, and then 0, 0.5, 0.3, and then negative 160, 0, negative 120. So that's going to be, we select I, we cancel out row and column containing I. Negative 120 times 0.5 is negative 60. 0 times 0.3 is 0, minus J, we cancel out row and column containing J. Negative 120 times 0 is 0, minus negative 160 times 0.3 gives negative 48. So that becomes plus 48, and then plus K. We cancel out the row and column containing K. 0 times 0 is 0, minus negative 160 times 0.5 is negative 80. So it becomes plus 80. So this is equal to negative 60I minus 48J plus 80K. So that is for M2. So lastly, we can find or we can determine the resultant couple moments about O if we add all these three quantities, which are M, M1, and then M2. So we have M, negative 75I, M1 plus 30I, and then plus M2. So we have plus negative 600I minus 48J plus 80K. So that is equal to negative 75 minus 60 is negative 135 plus 30. So that becomes negative 105I minus 48J plus 80K. Now we have this in Newton meter. So this happens to be the resultant couple moment about point O. So that's it for today's video. Thanks for watching and see you in my next video. Bye bye.